Greetings and welcome. In this section, we are going to work on two questions from the DBE 2023. These questions are based on matter and materials, which is organic molecules. So we are going to work on two questions, question 2 and question 3. So the question 2 goes as follows. Study the table below and answer the questions that follow. So we are given some organic molecules here, and we are requested to define the term unsaturated hydrocarbon. So we have got question 2.1. So what are unsaturated hydrocarbons? Unsaturated hydrocarbons are compounds. These are compounds. So unsaturated hydrocarbons are compounds with one or more multiple bonds between the carbon atoms in their hydrocarbon chains. So here we are referring to, if we look at the homologous series that we have studied, which are alkanes, alkenes, alkynes, haloalkanes. So we are looking at those homologous series that have got double bonds. That is what we refer to as multiple bonds or triple bonds. So these are compounds with one double bond or more, or one triple bond or more. Okay. 2.2. Write down the letter that represents an unsaturated hydrocarbon. So we have got A, B, C, D, E. So which letter is an unsaturated hydrocarbon? As we can clearly see, there is no multiple bond here. In A, double bond or triple bond. In B, we don't have any double bond or triple bond. So this is saturated. B is saturated. Also, C is saturated. If we can, this can be an aldehyde or a ketone. Okay, and D, when we look at D, looks like it is unsaturated, but for you to see this clearly, let me just draw out what this means. So this is written in the form what is called the condensed structural formula. CH3, then bracket CH2, CH2. So what you might need to do here is to draw this one in the form of a structural formula. This is in condensed structural formula. This is a condensed, okay, structural. So we want to draw it in the structural formula. A structural formula is just a formula that shows the atoms that are attached to which in the molecule. So you are actually drawing it like here we have got a CH3. It means we have got a C carbon atom attached to 3 hydrogen atom. Okay, so that's what we have here. And then this is bonded to CH2. And how many CH2? We have got 4 of them. So we can have 1, 2, 3, 4. Okay, and each C has got 1 H there, 1 H. That is CH2. Okay, I'm just drawing this to illustrate why it is an unsaturated. Okay, so, and then that is CH2, 4 of them is bonded to C with an H. So another bond here, C, but there is 1 H there. Okay, and bonded to a carbon chain, a carbon atom again with the 2 hydrogens. So bond to carbon with the 2 hydrogens. We usually write them at an angle there. All right, so that is what the condensed structural formula is telling us here. Now, considering the fact that a carbon atom has got 4 covalent bonds, which means it can form a maximum of 4 bonds with other atoms. So if you notice all the other C's here, the first 5 C's, they all have 4 covalent bonds around them. Okay, there are 4 bonds around C. But if you look at this one here, there are 3 bonds, and the last one is 3 bonds, implying that we need to have a double bond at the end there, so that this C here will have 4 and that will have 4. So which makes it to be an unsaturated hydrocarbon. Of course, you don't have to write this one in your formula as part of your answer. I'm just writing this out so that I can explain it. But to answer your question, since they want you just to write the letter here, the letter that represents the unsaturated hydrocarbon, as we have seen that D is our answer, so we'll write 2.2D. Okay, that is our answer, and that is just part of the expansion to explain that. And then 2.21, so this is 221, and 222, we are required to write down the IUPAC name of compound A. The IUPAC name of compound A. So we know from the rules of the systematic rules that we use for naming the hydrocarbons, first we need to take note of the longest chain. Okay, what is our longest chain here? Okay, so we can take this C here, I'll highlight it with that red line, and then this, and then that. Okay, you can make a bend here, but it's fine. So that indicates that we have got 1, 2, 3, 4, 5, 6. So remember, there's free rotation around each C, so we can have an angle there. That is okay. So which means here we are dealing with a hexane, because the longest chain is a C and they are all single bonds. So that is a hexane. Okay, and then the rest, these other C's here, this one and that one, which are not along that chain, they are our substituents or our branches. So in naming this hydrocarbon, so first of all, we have to indicate this is our prefixes. This branch here, our branches are methyl branches. So where is our methyl branch? Is on carbon number 2. Remembering that our C here, this C, we can number the number of C's as this carbon number 1, and this carbon number 2, carbon number 3, carbon number 4, and carbon number 5, carbon number 6. We number the carbon atoms starting from the one that is closest to the branch. Okay, so this C here on our right, it is closest to this branch, our methyl branch. So that is our carbon number 1. Okay, so that's why we are considering carbon number 1 there. So now let's come now to writing the name down. So what we have here is we've got a methyl at carbon number 2 attached to carbon number 2. So we'll write it as 2, because there's another methyl at carbon number 4 here, which is 2, 4. So we've got the 2 methyls, and we put a dash there because we are about to write a word. What is our word? We've got 2 methyls, so we have to write it as dimethyl. Okay, and this is in a chain of a hexane, so this is hexane. So which means our full name is 2, 4 dimethyl hexane. Remember the 2 and the 4, these are numbers. You separate them by a comma, and between a number and a word, you separate with a dash. So we have a carbon number 2, a branch at 2, a branch at 4, so it's 2, 4, and we've got 2 branches. We use dimethyl. So our methyl is our branch in a chain of hexane. So that is the full name for that, 2, 4 dimethyl hexane. Then 223, write down the IUPAC name of the positional isomer of compound B. The IUPAC name of the positional isomer of compound B. So here is our compound B. Now a positional isomer is just these are compounds that have got the same molecular formula, but they've got different positions of the side chain, or it can be different position of the substituent, or different position of the functional group. So meaning that here we have got a functional group which is OH, our hydroxyl group here, it is on carbon number 1. Again, when we name our when we number our carbons, we number our carbon starting from the one closest to the functional group. So our functional group is hydroxyl group, so we number it, we number our carbons starting from there. Okay, so since it is a carbon number 1, if we want to write a positional, so we can change the position of hydroxyl group. So if we choose to place it here on carbon number 2, okay, so that will make it to be a positional isomer. So I can just illustrate it here. If we were to write the positional isomer, again, you don't have to write this as part of your answer. That is a C, C, C. Okay, so I have 1, 2, 3, but I have removed the hydroxyl and I have put it in the second, the middle C here. So I'm going to have my hydroxyl over here. Okay, and then I'll have the H there, and this one will be the H, H, H. Of course, this H that was here is swapped with that hydroxyl. Okay, so we have something of that sort. Okay, so that will be a positional isomer, which means they will have the same molecular formula but different positions of the hydroxyl group. Now what they want here is to give the IUPAC name, which means what is the name for that. That is what we need to write as our answer. So to write as our answer, the answer to that one, what is the name for this one? This one is a propanol. Okay, propanol. But where is our propanol? Our hydroxyl. Our hydroxyl is on carbon number 2. So we write it as propan, then 2-O. Okay, so the position of the substituent is indicated by the 2. Right, so the IUPAC name is a propan 2-O. That is a propan 2-O. And then 2.3, 2.2.4, we are required to write down the IUPAC name of compound D. Compound D here. Okay, let me just clear off this. Now compound D, it's good that we have expanded here. Compound D is here. So from the structural formula, we can see the name here. So first of all, we have to identify what is our longest chain. 1, 2, 3, 4, 5, 6, 7. So, and we have got a double bond here. So because we have got 7 Cs, so that is a heptene. So that is a heptene. And remember, in an alkene, we need to indicate where is our double bond. So our double bond is after the first carbon. So we can write that name as the hept. Okay, and we indicate the position of the double bond. 1 is after the first carbon. Okay, and the suffix is ene. So compound D, the IUPAC name is hept1-ene. So the full name for compound D is hept1-ene. Again, remember, whenever you write a number and letters, they are separated by a dash. That's why we've got those dashes. Okay, hept is our stem or our root, and then ene is our suffix, the ending for alkenes, and then 1 indicates where is our double bond, which is the functional group for alkenes. Okay, so that answers 2.24 and 2.25. 2.25. We are required to write down the balanced equation using molecular formulae. Okay, we are required to write down the molecular formulae for the complete combustion of compound A. Okay, so one thing we know is when we talk about combustion, we are reacting we are burning a substance in oxygen. So now they want the molecular formula. What we are given here for compound A, this is a structural formula. Remember what we said, the structural formula? It shows which atoms are attached to which in the molecule. So we've got C attached to C, C attached to H, something. So that is a structural formula, more like a skeleton part. But now we are required to use the molecular formula. The molecular formula is the formula that indicates the type of atoms and the actual number of each atom in the compound. So we are going to say, okay, what are the types of atoms we have here? We have got carbon, so we indicate the C there. Okay, so that is a C. And how many C's are there? Okay, 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 C's. Okay, and hydrogen, how many hydrogen are there? Okay, that is 8 times 2 plus 2. Remember the general formula for alkanes, because these are all single bonds. So we have got 18. Okay, you can count them here. 8 times 2, 16. 16 plus 2, 18. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So which means we are indicating that there is C8, 8 carbon atoms and 18 hydrogen atoms. That is what we call a molecular formula. Now we are burning it. Okay, under combustion, so it's oxygen, so it's plus O2. Right, oxygen is diatomic, so it's always 2 oxygens, and then giving us always, we must know that, we are expected to know that when you burn a butane, alkanes, mostly alkanes and alkanes, the product that we get there, here we are given that it's complete combustion. Okay, so if it is complete combustion, which means there is all the energy that we have, so we are going to form 2 products, which are carbon dioxide plus water. So we have carbon dioxide plus water plus energy, of course, heat and so on. So these are the molecular formula for the reactants and the products that are involved in this equation. But now we must balance out. Balancing it means that we are applying the law of conservation of mass here, that on the left, in our reactants, we need the same number of atoms for each element, meaning that I've got, for example, I've got 8 carbons here, so here I've got 1 carbon, so we need to balance out. And we balance out by writing a coefficient, a number in front of the molecular formula. So what we can do here is, here I've got 8 carbons, so here I've got 1 carbon, so I will multiply by 8. So you write an 8 there. So 8 times C, 8C. Then I would do C8. Okay, so we have balanced the carbon. Start with those that appear once on either side. Like here I've got 1 carbon atom, 1 carbon atom, 1 hydrogen atom, 1. That's why I start with carbon. Okay. The oxygen is not a good choice to start with, because here I've got 1 oxygen. It is appearing once there, but here it appears twice. So always take the oxygen to be the last one. Okay. If you go through the tips for balancing chemical equations, you get to know that. So I've balanced my carbons. Now I'm going to balance my hydrogen. Hydrogen, I've got 18 here. So here I've got a 2. Now the 2 will multiply. So what should I multiply? Remember what a coefficient means. A coefficient, I must multiply the 2 by that number here to give me 18, which means I need a 9 over here. Okay, so 9 times 2, 9 hydrogens. That's what we have. Now, having done that, we can now come to the oxygen. Here I've got a 2 oxygen here, and I have got here 8 times 8 oxygens, carbon dioxide here. So I've got 16 plus 9, which will give me 25. So it means here, what do I need to get 25? I need 12 and a half. Okay, divide that by 2. Usually I will just say write 25 there and then divide by 2. Okay, so this is 12 and a half. But now we are not allowed to write a decimal number as a coefficient. So what do? We eliminate the 2 by multiplying throughout all the molecular formula. We multiply them by the 2. So meaning now I'm ready to write my final answer. This is just like working rough work there. So my final answer to that will be, if I multiply by 2 here, I'm going to have 2C8H18, okay, plus, if I multiply 20 over 2 by 2, that will leave me with a 25, so I have 25O2, okay, which will give me the carbons. There was an 8 here, so that 8 will multiply by 2, that will give me 16 carbon dioxide, and there was 9 here times 2, that will give me 18 water. Okay, so now you can see that here they are balanced now, so our answer will be 2, this one, 25, that, and that. So that will give us the final answer to that. Okay, so this one is more like a workout to come to this answer. So if you check here, 2 times C8, that is 16. Here I've got 16 carbon. How many hydrogen? 36. 2 times H18, 36. Here how many hydrogen? 80 times 2, 36. How many oxygen? 25 times 2, 50. Here how many? On the right, 16 times 2, that is 32 plus 18, that will give you 50. So now it's balanced out. Okay, but the bottom line is to know that butane or an alkane plus oxygen, you get carbon dioxide plus water. Make sure that you know your formulae there for carbon dioxide and water. Right, so that answers that part. Let's come to the next question. So we have written the balanced equation here, molecular formula, and now then it comes to 2.3. The formula C4H, this one, represents the compounds that are functional isomers of each other. Define the term functional isomer. 2, 3, 1. So what are functional isomers? Remember, we talked about positional isomer. We also have chain isomer. Then we have got functional isomer. So a functional isomer, I'll write it down here. And these are compounds. These are compounds. So I've written here that functional isomer, these are compounds. Usually we are comparing two, so that's why you say in plural here. These are compounds that have got the same molecular formula but different functional groups, and therefore belong to different homologous series. So what we are saying here is they have got the same molecular formula. Remember what a molecular formula, just like what we have written here. A molecular formula, it shows the type of atoms and the actual number of atoms that we have there. But they have got a different homologous series. So coming down to this one, we have got a C4H8O. Okay, that's a molecular formula there. So we might have two compounds that have got the same formula, but they belong to different homologous series. In other words, they've got different functional groups. Remember, what separates homologous series are the functional groups. When you talk about homologous series again, remember we are talking about alkanes, alkenes, alkynes, haloalkanes, aldehydes, alcohols, carboxylic acids, ketones, esters. So those are homologous series. So what makes them different are functional groups. So if they've got different functional groups, which means they belong to different homologous series. Okay, so that's what we have. So write down the functional, the structural formulae of each of these two functional isomers. So what we are given here is, we are given this molecular formula 232. We are given the molecular formula C4H8O. Okay. For some of you, you might have picked up that this formula C4H4, this can be an aldehyde or a ketone. This is a molecular formula for an aldehyde and a ketone. And this aldehyde has got a four carbons, 8 hydrogen, and so on. Well, I'm going to explain this on the structural formula. So if we take, for example, if we consider that it is an aldehyde, so to answer that one, we will have first of all, let's say it is an aldehyde. So we are going to have C, because there are 4 C's here, and then I'll put in the H atoms, the covalent bonds there, H, and then this one will also have H, this one will have H, this one will have an H. Okay, this one will not have an H. Yeah, yes, we have an H there, an H there, and then the last one we have a carbonyl bonded to a hydrogen. Okay, so if you count here with 1, 2, 3, 4, so you got 4 C's. You count the H, there will be 8, and there's 1 oxygen. So it's an aldehyde, and we call this one a butanol. Okay, but that is not part of the answer. They are not asking us to give us the name. They're asking us to write down the structural formula. The structural formula. So this is the structural formula that they want, and one of them. And we're gonna write the other structural formula. The other structural formula from here is a ketone. Now a ketone would go 1, 2, 3, 4. Okay. Now what happens with a ketone is, let me just delete this one here, the H, right? What happens with a ketone is that you see this one here, this bond here, set of atoms. This is we'll call it a carbonyl. Okay, this is a carbonyl group. It's a carbonyl group. So now, when it is an aldehyde, the carbonyl group is bonded to one H. There must be an H there, which will make up what is called a formal group. So that's a carbonyl group. But now we want to change this one to a ketone, which is a functional isomer now. So to make it a ketone, I will just move this hydrogen here, or the oxygen, put it here, and then this H will come there. Okay, just swap these two, so that the carbonyl now is between 2 carbon atoms. So I will put my carbonyl here. I hope you are following me there. And then here the rest will be H, 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 and then there will be an H there, an H there, an H over here, an H over here, and an H there. Okay, so now you will see that the formula will still be the same, 4 C's, if you can count them, the H, and 1 oxygen there. So, but now this one, our functional group now is a carbonyl between 2 C's. Here it is a carbonyl bonded to 1 H. So now when it is like this one, it becomes what is called a ketone. Okay, and the specific name for that one, the IUPAC name for that one, it will be a butanone. Okay, that is a butanone. But now we also need to indicate where is our carbon now. So it's a butan 2-on. Okay, so which means our carbon now is attached to the second C. So it's a butan 2. So these are the names, but to answer the question, your marks, you get them from this one and that one. Those are the structural formulae, okay, for each of these. So they have got the same function, same molecular formula as we have explained earlier, but they have got a different functional groups. They have got different functional groups. Now, let me also mention here that when you are given functional groups out of the homologous series that we have, let me just complete this list. We've got aldehydes, we've got ketones, we have got carboxylic acids, we have got esters. Now, these last two here, the carboxylic acids and esters, they are functional groups of each other. Okay, and aldehydes and ketones, they also make functional groups. What I'm saying is, if you are given an aldehyde and they are asking you a functional isomer, so your answer automatically will be a ketone, and vice versa. Okay, so if you are given a ketone, its functional isomer will be an aldehyde. If you are given an aldehyde, its functional isomer will be a ketone. Why? Because they all have the same general formula, CnH2nO. Okay, they have got this general formula. Now, when you are given a carboxylic acid, okay, and they are asking you to find a functional isomer, so you must automatically know that your functional isomer will be an ester, okay, and vice versa. Why? Because the general formula here is CnH2nO2. Okay, there are two oxygens over here. So that's one thing also that you must take note about functional isomer, but this works only for functional isomers. So now we have got our answers over here and the other here, the structural formula for the two functional isomers. Let's come to question 2.4, the last on this section, 2.4. A 2-gram sample of compound E contains 1,09 gram carbon and 0,18 grams of hydrogen. The molecular mass of compound E is 88 grams per mole. Now let's take the these details here. So we are given that it's a 2-gram sample of compound E. Where is compound E here? Compound E is this one. It's just a hypothetical formula. CX, which means we don't know the number of carbons, HY and OZ. Okay, so let me just write down here 2.4. 2.4. So we are given CX, HY hydrogen atoms and Z oxygen atoms. Okay, so that's just a hypothetical formula we are given here. So we are given that a 2-gram sample of compound E contains 1,09 grams carbon and 0,18 grams hydrogen, and the molecular mass of compound E is this one. Okay, let's jot down let us jot down that one. So I'd say 2 grams. This is made up of what? 1.09 hydrogen and how much? 0.18 hydro, oh, it's actually hydrogen. 0.18 hydrogen. This is carbon. This one is carbon. And I guess we can calculate the, so if 1,09 is carbon and 0.18 is hydrogen, so remember there's oxygen also here, so how much will be oxygen? So the balance will be oxygen, so that will be how much? We need that one for our calculation. Let's go there. So it's gonna be 2, okay, let me just open one there. Right, so we will have here 2 minus 1.09 plus 0.18. Okay, let me just separate that one. What is 0.73? So that would be 0.73 grams of each. All right, so you will see why we need these numbers. So what we are going to do here is, okay, let me just lay out this work as follows. We need to calculate the percentage. What percentage is each element, okay, in the 2 gram? So let's look at carbon. Percentage carbon. Okay, what is our percentage? So we are going to have, okay, we can put an equal there. That is, I've got 1,09 out of 2 grams times 100. So what is our percentage there? So let's calculate it. 1.09 divided by 2 over 2, okay, multiplied by 100, okay, 100 there. What do we have here? I've got 54.5, so this is 54.5%. okay, so what is the percentage of percentage hydrogen? Again, we're gonna do that one. So I've got how many hydrogen? 0.18 out of 2, okay, multiplied by 100. Let's see what percentage we have here. So 0.18 over 2 and then multiplied by 100, then multiplied by 100 there. We are having 40%. Okay, that is 0.18. Okay, so that will give us 9%. 0.18 over 2 times 100, 9%. That is 9%. That makes a reasonable answer. And then let's calculate the percentage of oxygen. What is our percentage of oxygen? How much oxygen is there? 0.73 over 2 multiplied by 100. Or you can simply add these two, then separate from 100, then you can get your answer straight away. So let's just do it the way 0.73 over divided by 2, then we multiply by 100. What am I getting here? 36.5. So this is 36.5%. Okay, so now we have calculated these percentages. So what we are going to do here is I'm going to write them as the ratio in terms of their moles. Okay, so I'll assume, let's say, let me just put it here as I've got my carbon and I've got my hydrogen and I've got my oxygen. Right, so now these percentages, I will take them to be grams. So I will say, okay, if I have got 54.5 grams. So how many grams would I have for hydrogen? I've got 9 grams of hydrogen, and I have got 36.5 grams of hydrogen. You will see why I'm converting these ones to grams. It's more like a proportion. Okay, now why am I using this one is that now we want to see the mole ratio, the ratio of the moles. There's a formula that we use, which is N number of moles is equal to mass over molar mass. Mass over molar mass. So what we are going to do here is I'm going to calculate what would be the ratio of the moles. Okay, what are the moles that we have here? Now 54.5 is my mass, so I'm gonna divide that by the molar mass of carbon, and then 9 is this one, and we do the rest. So the molar mass of each of these compounds, we get them from the periodic table. Okay, so I've got the carbon here, we have got the oxygen there, and the hydrogen is over here. So the molar mass is this number at the bottom here, which is referred to as the relative atomic mass. Okay, the atomic mass for each. So we divide that number because we want to find the number of moles. So we are going to do that. So we can say, okay, let's look at our ratio here. Or just say our ratio and ratio. The reason why we are doing this is why we are calculating all these ratios, because we want to see what is called the empirical formula. The empirical formula. So we will go on to say 54.5, so 54.5 divided by the molar mass of carbon, which is what? 12. Okay, from the formula here, carbon is 12. So our carbon is 12 there, so we divide. And our answer, and this one, it will be 9 divided by 1. The molar mass of hydrogen, and this one will be 36.5 divided by molar mass of oxygen is 16. That is 16. And that is 16. So let's see the answers that we'll get from here, which is going to give us how much. Okay, calculator 50, 54, okay. 54.5 divided by 12, we'll get 4.5416. okay, so we have got a 4.5416. so we have got a 4.54 moles of carbon. Okay, and then 9 over 1, that is 9. Okay, so we've got 9 here, and 36.5 over 16. Let's divide again. 36.5, 36.5 divided by 16. That will be answer they change 2.2812. okay, 2.2825. so that's what we have. So the numbers that we are getting here is the ratio of the moles, because remember we took our percentages to represent mass grams. Now we are dividing by the m, molar mass, so we'll get the number of moles. So for every 4.5 moles of carbon, which is the number of particles of carbon, then we've got 9, we've got this. Now to find the ratio of these carbons, now we have to reduce this one in its simplest form. So we divide this by 2.28125, which is 1 ratio in simplest form, and I divide this one by 2.2815. Okay, so let's divide again. 9 divided by 2.2815. So what do I get? 3.9. This one, let's write it off to the nearest, which is a 4. Okay, that will be a 4. Okay, and then 4.5 divided by that 2 again. Let's divide there. 4.5416 divided by 2.28125. Answer is 1.999. Okay, to the simplest, that will give us a 2. Okay. So which means now we have got the estimated ratio of 241. Now the 241, the ratio, will give us what is called the empirical formula. The empirical formula. Now what do we mean by empirical formula? The empirical formula is just the formula of a compound which indicates the simplest whole number ratio in which the different elements are bonded with each other. So they give us the simplest ratio in which these elements are bonded together: the carbon, hydrogen, oxygen. So our empirical formula is going to be, for carbon, I've got 2 carbon atoms, and hydrogen I will have the 4, and oxygen I will have 1. So I will have C2H4. Okay, for this is what is called the empirical formula. Now after finding the empirical formula, we are going to let's come back to the question here. What is saying? We are given that the molecular mass of compound E is 88 grams per mole. The molecular mass of compound E is 88 grams per mole. Okay, I'll move this one down. Now we are given that the molecular mass for that compound C, X, H, Y, and O, Z, which means if we add all the molar masses, if we find the molar mass of this one, we are going to get the M molecular mass for this one is 88 grams per mole. But now this 88 grams, it will tell us how many empirical formulae are there. Now to do that, we need to find what is the molecular mass of our empirical formula. So I will do this M, the molecular mass of C2H4O is how much? So we are going to add up we have got 2 carbons, so that will be 2 times 12. Remember, the molar mass for carbon plus hydrogen. There are 4 hydrogen here, so 1 times 4, because each hydrogen has got 1, plus oxygen, it's 1. It's 16 there. So I'm going to get 24 plus 4 plus 16, which will give us 44. So 44 grams per mole. So now to find remember the question is asking us to calculate the structural or the molecular formula. Okay, the molecular formula for this compound. To find the molecular formula of the compound, we need to see now how many empirical formulae are there. Okay, so how many empirical formulas? If C2H4 is 44, so how many are there in 88? So if you do your division there, that will, you take 88, the molecular mass for your compound 88, then divided by the molecular formula for mass for your C2, the empirical formula, which is 44. So this will give you a clue that I need two of them. So what you need to do, what you do here to find the formula, therefore the formula CX, H, Y, and O, Z will be equal to, now these two simply multiply by the 2 here. So we are going to have C4, H, 8, and O2. Okay, so we have C4H8O2. So this is our molecular formula for that particular. So to go through the process again quickly, so calculate the percentage of each element. Okay, and those percentages will give you the ratio of the mass of each in grams of the mass of each element. Carbon, I've got 54.5, hydrogen. Then find the ratio of the moles. Divide the percentages by the molar mass, okay, which is the M, to find the ratio of the moles. Then the ratio of the moles, take the smallest number of that ratio, okay, and then you divide it into that one. It's more like if you are given a ratio, let's say it's 10 is to 6 is to 4, and now they say write down the to its simplest form. So you just divide by 4 by 4 by 4, okay, so that you get 1 is to something something. So you just have to do that. So take the smallest number, divide by that number, and then into this. So 1, 4, 2. That will give you the empirical formula. And then just take the molecular mass for your empirical formula, divide it into the molecular mass for the formula that you are looking for. Okay, we are given that the molecular mass for this one is 88. So divided 2, then that shows you that I have got 2 of these. So I would C2, so multiply there to give you your answer over here. Okay, I hope you follow that one and trust that it makes sense for now. All right, let's go to, that it brings us to the end of this section. You can see it's quite some marks there, 25 marks. Let's jump into another question. Question 3. Question 3 reads as follows. Learners investigate the boiling points of the 4 organic compounds given below. So we are given the compounds here, butanol, 72, 74, this is the molecular mass. And then define the term boiling point. So this is a standard definition that you must all be aware of. Boiling point, this is the temperature at which the vapor pressure of a substance is equal to the atmospheric pressure. That's the definition for boiling point. 3.2. Which compound butane 1-ol or 2-methylpropanol will have the higher boiling point. Fully explain the answer. So when you take butane 1, this is an alcohol. 2-methylpropanol is also alcohol. And when you consider the fact that they all have, this is one here, they all have the same molecular formula. Remember the factors that affect the boiling point of a substance. We've got the intermolecular forces, we've got the molecular mass, we've got the chain length, okay, which is the degree of branching, and we also have the functional group, okay, the number of functional groups in a substance and so on. So here we have got the 2-methyl is an alcohol, and butane 1 also they've got this. But what makes them to be different in this case? Okay, which one would have a higher boiling point and why? Now to explain this one, you'll see we are going to expand here. Let's draw up the structural formula for butane 1 and the 2-methylpropanol. That will explain how we can explain the difference in the boiling point. So butane 1 is simply this. Again, you don't have to write that down. This is just for explanation. Okay, so it's a butane, that is 4 C's, and we have got some hydrogen all over there. Okay, hydrogen. So this is a straight chain. Okay, now so that's a butane 1 because the hydroxyl group is bonded to one carbon chain, one carbon atom. Now let's come to 2-methylpropan-1-ol. Okay, propanol, which means we have got the 3 C's, so we have 1, 2, 3. Okay, and where is 1-ol? It means our alcohol is on carbon number 1, so I'll put again our alcohol on the first carbon here. It can be this one or that one, and 1. And then at carbon number 2 we have got a methyl, so at carbon number 2, so we'll put a methyl here. Okay, right, that's what we've got, a 2-methyl propan 1. So the rest are H, so we've got H, H, H. Now, so out of these two, which one would we say has got a higher boiling point and why? So they all have the same molecular formula. If you can count the number of C's and the number of H, the oxygen are the same. So they have got the same molecular mass. But the difference between them is the degree of branching. Okay, here we have got a straight chain of C's, and here we have got a C's, but there's a branch over here. So that is a factor that will cause these compounds to have different molecular, to have different boiling points. Okay. So there's a branch of the carbon atoms. So now what are we going to write here? So 3, 2 would say the one that we have a higher boiling point is butanol. Okay, so our answer should be butanol. To answer that one, butane 1. Oh, okay. So why is this one having a higher boiling point and this one has got a low boiling point? I'll pick this one. I will take the 2-methylpropanol and say that this one has got a lower boiling point than that. Why does it have a lower boiling point? So I will say that 2-methylpropan-1 yes, more branching in the carbon chain. So if it has got a more branching in the carbon chain, what effect does this have? So say the more branched it is, the more branched it is, or the more branched a carbon compound is, so we are saying here that the 2-methylpropanol has more branching in the carbon chain. So the more branched it is, the more spherical the structure is. The more so it is more round, okay, it is. So this one is more round than butane one. So if it is more round, it has got a smaller contact surface. So it has got a smaller contact surface. Thus, it has got weaker van der Waals forces, okay, between the molecules. So thus, the weaker the van der Waals forces between the molecules, and therefore it has a lower boiling point than butane 1O. Okay, so that is how you explain. Or you can say butane 1O has got a higher boiling point. Why? Because there is no branching in the carbon chain. You are more or less writing the opposite of what is here. So there's more branching. You got a straight chain. So the less the branching it is, therefore the less spherical it is, and therefore it has got a larger contact surface area, and therefore there are stronger van der Waals forces between the molecules, okay, and therefore it has got a higher boiling point. So that's what we have here. Now then, question. So we are answering 3.2. I guess you get your marks from there. 1 mark for explaining butanol, and then 1 mark for identifying your compound, and then the 3 marks for explaining. Now the curves P, Q, R, and S below were obtained from the results of the investigation, and X represents a specific temperature. Which physical property is represented by temperature X? Okay, so temperature X here. Now when we look at temperature X, it is a temperature at which this compound P is now level. Okay, in other words, the temperature is constant. So when we take the time, or the time versus temperature coordinates, and when you identify that your temperature remains constant, the stage at which, or the temperature at which it remains constant, the time at which it remains constant, it means at that stage the substance has reached a boiling point. So we are simply saying that X here is representing the boiling point of compound P. Why? Because our temperature at that stage is remaining constant. So 3.3, the physical property represented by X is the boiling point of compound P. We know what it is because from these 4, compound P, the one that has got the highest boiling point out of all these ones is the butanol. Butanol is the one that is what it's an alcohol. So alcohol has got this strong hydrogen bonds, so it has got the highest boiling point. But anyway, let's leave that one. So 3.3 is indicating the boiling point of compound P, that is the physical property that we have here. Then 3.4, which curves P, Q, R, and S represents butanone, propanoic acid, and 2-methyl-propan 1-O. Okay, give a reason for the answer to question 3.42. Now here, what you can do is, okay, let's identify them according to the homologous series. Butanone is a ketone. Okay, this is a ketone, and this is a propanoic acid, is a carboxylic acid. Carboxylic acid. And the 2-methyl-propan, that is a alcohol. And yeah, okay. And I can add here butan 1, or it's also alcohol. Now, when you arrange these ones in terms of their strength, of their forces, the intermolecular force, you'll find that the ketone is the weakest one, because here we've got dipole forces. It has got some weak van der Waals forces, the ketone. Okay, and then carboxylic acid, it has got hydrogen bonds, and alcohol, and they also have hydrogen bonds. But now alcohol has got a stronger hydrogen bonds than the carboxylic acid. So if we are to arrange them, put them here, we can put them as the lowest graph, which has got the lowest boiling point. This one would be a ketone. Okay, because it is the weakest. So which is our ketone here is our butanone. So you can see that the curve S is for butanone. Okay, and then the second highest boiling point after the ketone is the carboxylic acid. So R will be the carboxylic acid. And what is our carboxylic acid here? It's a propanoic acid. So propanoic acid is going to take graph R. Okay, and P is the one that has got the highest boiling point, which is the butan 1-O. Butan 1-O. So Q would be our 2-methyl-propanol. So Q is alcohol. So this is an alcohol which is 2-methyl. So this one will be a Q. Right. So we have literally answered that one. So we are going to have 3.4.1. Let's write down our answer. 341. So our butanone is S. Okay. 342. Our propanoic acid is R. Okay. And 343. Our 2-methyl-propanol is 2-methyl-propanol, we said it's Q. So that is Q. And P is our butanol, which is with the highest boiling point. Now, question 3.5. Okay, 3.5. Give a reason for the answer to question 342. Okay, 3.5. Give a reason the answer to 3.42. Okay, 3.42. Well, I guess this question is trying to ask us, okay, why are you putting the propanoic acid? Why are you putting the propanoic acid above the butanone and below the 2-methyl, below the alcohol? Okay, so why is it where it is here? So give a reason why it has to take that position. There's 1 mark for that. So we can say that here, just to answer here, we can say propanoic acid has stronger hydrogen bond. We can say stronger intermolecular forces than ketones, which is our butanol. So therefore it has got a higher boiling point than the ketone, but it has weaker intermolecular forces than alcohol. Intermolecular forces than alcohol. So what does that mean? It means it has got a higher boiling point than a ketone, and therefore it has got a less boiling point, a lower boiling point than alcohol. Therefore, you can put it that way. Therefore, it has a higher boiling point than ketones or butanol, and a lower boiling point than alcohols. Okay, so that will give us the final answer to that. Okay, so that brings us to the end of these two questions. I hope you learned something.